Okay, so we have Javier Serrano from Brown, who will talk about existence of non-convex bit states.
Okay, thank you. Thank you, Camilos, both Camilos, for the invitation, and thank you everyone for coming here today. So today I won't talk about any AI-related stuff. There will be computers involved in the talk. But no AI. So everything I will talk about today is joint work with Gerard Castro Lopez, who was an undergrad 2 years ago, visiting me at Brown, and this is kind of a senior undergrad thesis. So the whole theme and the whole topic is going to be the construction of certain solutions to PD. I'll be more specific, that are non-convex. Okay, so a small advertisement. So this is Gerard, and last week for this work, he got the best work by an undergrad or master student in Spain. Across all fields of science and humanities, like super first prize of the jury, which is usually very, very difficult for a math project, because you are competing with like bio and it's difficult to make a point to the jury to evaluate these types of works. Okay, so this was just announced last week. Okay, so the bottom line of what I will talk about is essentially the problem is less important. This is more about the technique. So focus on the method and not so much on the result. I mean, the result is nice, but the applicability of the method is what I would highlight here, rather than the result on its own. So this is this is going to be widely applicable to many situations, many equations, many types of solutions, and the main idea is that this is in some sense it's non-perturbative analysis. Okay, it will be somewhat perturbative, but it is going to be non-perturbative, at least non-perturbative from something that we understand well. It will be perturbative from something that we don't understand at all. So that's sort of the main ideas and the main description of this kind of strategy for this problem. Okay, so I'm going to be talking about solutions of 2D Euler. In this audience, I mean, this is 2D Euler in vorticity formulation. I don't think this really needs an introduction. So omega is the vorticity, psi is the string function. We can recover psi by means of from psi via inverting the Laplacian, and then if we take the perpendicular gradients, we can write the velocity u as a singular integral acting on omega. Okay, so no big surprises here. We're going to be trying to look for solutions or certain solutions of 2D Euler. I'm going to be more specific. I'm going to be looking for solutions of patch type. So the vorticity is going to be a characteristic function of some domain on the plane, 0 outside, and then the dynamics can be rewritten in terms of the boundary of the patch that I'm going to be parameterizing here by z. And then, okay, this is the normal velocity of this free boundary, and this evolves according to some singular integral operator defined on the curve, which has a logarithmic singular. Okay, but we can characterize the dynamics of the PD just by understanding well how the boundary moves, and we don't need to really care too much about the interior.
Alpha is
a parameter parameterizing the curve. So the curve is indexed by alpha at t is time, and alpha goes from -pi to pi, and it's just the coordinate in which we traverse the curve.
Do you specify it's a constant speed parameterization, or
It doesn't need to be.
it doesn't need to be?
No. No, I could change if I added terms here in the tangential direction that could potentially affect the reparametrization, but I'm not really even looking at how the particles move in the tangential direction. Okay? So for now, it's not. It may be sometimes useful for numerical purposes, but here it's not even going to be necessary to do anything clever about it. Okay, so from the point of view of regularity, for many years, people didn't know whether there was a global existence or not for these kind of problems, and some numerics suggested that there could be potentially a self-intersection. And then Schemann and Bertozzi-Constantin in the 90s proved that if you start in sigma gamma, then the curve lives globally in sigma gamma. Okay, so what are V-states? Okay, so I'm going to be talking and I'm going to be looking about V-state solutions. So V-state solutions are solutions to the previous equation that I wrote, that what they do is that they rotate with a constant angular velocity in time and in space. So the center of mass is fixed at 0, and then all they do is they just kind of rotate around the center of mass with the same uniform angular velocity.
And the patch remains with the same shape, really.
Yeah, exactly. So they are in the rotating frame, they are steady solutions. Exactly. So these were important in the beginning because those were the first examples when people didn't know whether there would be global existence or not. Those were the first examples that people constructed for which they knew that there were A, non-trivial, and B, guaranteed to have global existence.
Why are they called V-states?
B stands for vortex. I think the very first paper, and they were calling, this is the Dim and Sabuski paper, and they were calling them vortex states, and the V state. So that's pretty much the history behind the name. Okay, so let's impose that and let's see how our equation looks like. So we impose O is the rotation matrix with this angular velocity omega, and we impose that the curve essentially is steady in this rotating frame. And then what we end up having is, well, this sort of, we just substitute into the equation that we had before. So now there is no time anymore. We have the term coming from the rotation, has to be equal to this kind of nasty singular integral operator. Okay, so we need to solve now for, in principle, for omega and for z naught. This is the goal here. Okay, so what do we know concerning explicit solutions, or simple solutions, or easy solutions? So it is not very difficult to see that if you take a disk, then this is going to be a stationary solution, and in particular, it's going to be a rotating solution for any angular velocity. Okay? This is not very difficult. One can even see this from the perspective of the multiplier and the perspective of the velocity. So that was known for like many years. Then what it is slightly harder is to say, well, if I take an ellipse, then this is also a V-state. So not for any omega, the angular velocity depends on the parameters of the ellipse. If the semi-axes are A and B, then the angular velocity is going to be something like AB divided by A plus B squared. Okay, so this is a result of Kirchhoff, and he figured out that if you start with this initial configuration and you evolve time, then the shape of the ellipse will not matter, and it will rotate at the proper angular speed.
These are classical ellipses, right?
Yeah, this is I don't know, 100-year-old results.
It's an ellipse, and it was discovered by Kirchhoff
That they rotate.
Yeah.
Okay.
Yes. Yeah, this is why they are known as the Kirchhoff ellipses.
Okay. So, sorry, just a silly question. So somehow you're writing out your equation for the boundary.
That's right.
And you condition. So, but is there a flow within the domain which is like
the particles inside may move, but the the patch as a whole
is just
not
rotating rigidly.
That's right.
Okay.
Fine. It's not that the particles inside stay put. They will all move, but then the boundary will not be deformed by the action of the Euler equation. For these very special solutions, in general, of course, it will move, but here it won't. And this is the kind of rigidity that we're looking for. Okay, so maybe this is the interesting part of this slide, that besides these two results, no other explicit solutions are known. Okay, so these are, well, early numerics, 1978. This is the paper that I was mentioning before that coined the term V-states. So what Dim and Sabuski did with the computational, it's a paper in PRL. So with the computational technology that they had, they tried the following. They were looking for non-trivial V-states, and they took the disk, and then they found out that numerically they could bifurcate at certain angular speeds. So if you chose the angular velocity correctly, then there were like branch at certain speeds that were emanating from the disk with, in this case, threefold and fourfold symmetry, and creating these kind of shapes that are, let's say, non-trivial V-states. Okay, so this is for the threefold branch, and this is for the fourfold branch. Okay, so this is what they did about 50 years ago. Okay, and again, the one thing to keep in mind is that in '78 people didn't know whether this kind of problem had a global solution or not. Okay, this is a more sophisticated bifurcation analysis. This is the PhD thesis of Kam, who was a student of Safman in about 10 years after. This is 87. So the axes are a bit flipped with what is usually used. This is the angular minus the angular velocity. And these sort of solid and then dotted lines correspond to solutions. Never mind the vertical coordinate. But this horizontal line here corresponds to the disk. This line here is the line of twofold symmetry, which are the ellipses. Remember, the angular velocity was AB divided by A plus B squared. That's a number for any A and B that is between 0 and 1/4. So this precisely is the elliptical branch. Then we have the threefold branch, the fourfold branch, and so on. And then what Kam discovered was that in the elliptical branch, there were secondary bifurcations at certain points, depending on certain aspect ratio of the ellipse. Okay, this is still a numerical result from roughly 40 years ago.
So he's basically doing a linearization at these points, or like how they finding? They didn't have auto at the time, did they? So like how are they doing the
here the bifurcation from the disk? You can do pen and paper.
Yeah, that's fine. Yeah,
and then it will tell you sort of what is this value, what is this value. In fact, these values are m-1 divided by 2m.
Yeah.
Okay, so that's all right. And here you can do it by hand, and you get some sort of implicit equation which you can then solve, and then that will give you at least a fairly good approximation of the bifurcation point. It's not explicit like here, but you can find these points in an implicit way, and I think he found 5 or maybe a couple more. So you can do that, and then the real fight begins, because then you can you have to perturb a little bit and then make your continuation program to land on the secondary branch and not get trapped in the primary branch. Okay, so the heart of the matter and the difficulty here is not just to find these points. That's not, I mean, it's unpleasant, but it's doable. But rather land, once you do the continuation, into the actual secondary branch. Because as you see, the width here is fairly small. So it is, if you start, let's say, somewhere in the middle, then you need to do things carefully to land in like this secondary one rather than the first one. Okay. So let's see. I mean, all of these were like old pictures. Let's see what people have been able to prove over the years. So the first one to rigorously prove any of these pictures that we've seen was Burbia in '82. And also let me stress that the, let's say, bifurcation technology was not fully developed, or it was developed to a certain point back then. And he was able to prove local bifurcation at these values of omega. M here is the symmetry class of the bifurcating solution from the disk. Okay, so he was able to construct in a tiny neighborhood of these omegas, non-trivial, meaning non-radial solutions emanating from the disk. Guo, Holstrom, and Spearn proved that ellipses of a certain aspect ratio, if the aspect ratio leads to a very flat ellipse, are unstable. So the linear stable versus unstable bound was known since the end of the 19th century, but they upgraded it to the nonlinear instability. Then a couple of years later, Midi, Mateu, and Verdera improved the local bifurcation to prove not just that you bifurcate, but also that you are the boundary is C infinity, and it is convex. And again, this is somewhat expected, the convexity, because you are very close to the disk. So then, if you are perturbing the disk a little bit and nothing gets like too crazy, then you're still going to be convex. So you still have a little bit of room.
But this is a local.
This is what?
This is a local result.
Yeah. All of
Not
local.
Okay, because we know there's C1 alpha is global, but the convexity is only local.
The convexity is only local, and in fact, not true if you go to global. This is where I'm trying to get to, so we'll get there.
Okay.
So we improved on the C infinity regularity a few years later to prove that the boundary is actually analytic. And then there have been other local. At this point, everything, okay, besides the instability, which is not a bifurcation result, everything is a local bifurcation theorem. Everything only refers to a sufficiently small neighborhood of the disk at whatever angular velocity. So we did the same for the ellipses, constructing these secondary bifurcations of CAM that I showed before. Okay, so then the point in which you bifurcate is not so easy. It is defined in an implicit way, and okay, you have to fight. The operators are not diagonal, and you have to fight a little bit the construction and the spaces to make it work. But
when m is equal to 2, you get ellipses. What happens when you go to n equals 3? You showed us those pictures, but there's no explicit formula for it.
Right? No, unfortunately, besides the ellipses, there is no explicit formula for any sort of.
But each m has one such shape.
Yes. Yeah, one can prove bifurcation for at this value of omega m for all m greater or equal than 2. Okay, now up to here everything is local. Then Hassania, Masmoudi, and Wheeler did a global bifurcation result in the sense that they were able to construct a curve and keep going through the curve until something bad happened, and there are a couple of alternatives as to what are the bad things that could happen. So, for example, the interface may lose regularity and not be analytic or C infinity anymore, or other sort of potential bad things could happen as you get to the endpoint of the branch. Okay, we proved rigidity, meaning that in this context that there are no solutions beside the disk whenever omega is negative and whenever omega is greater or equal than 1/2. If you look here, there is an accumulation point as n goes to infinity at omega equals 1/2. So this is 1/2 minus 1/2m, and then there is nothing else beyond the 1/2. This is using completely different techniques, more related to calculus of variations. And then there have been other works by a lot of people, including global bifurcation or using KM theory to construct time quasi-periodic patches, or even look at other related problems like something called the Sadowski vortex, which has to do with translating vortices. So yeah, even in the last 5 years, people have been sort of working heavily in this area of this kind of rotating or translating solutions to the Euler. Okay, so this is sort of the mental picture that I always have. It's kind of an inverted diagram of what Cam did, but this is the way I like to think about this problem. So we have here this horizontal line is the disk, and then for the different m's, we can sort of bifurcate at this value omega m, and then there is a branch that, well, in this case goes all the way to 0, but here it presumably stops somewhere. This is still open. Okay. So what I want to understand is what happens kind of somewhere here, or even close to the endpoint. So this is sort of the type of problems that I want to do. And as I said before, if we take these little balls around the disk, then because they are close to the disk, in the right topology, the V states are going to be convex. Okay, but now I want to understand things kind of around here. So local bifurcation doesn't help me because these neighborhoods typically are very small, and I am in the non-perturbative regime. And global bifurcation doesn't help me either because I don't really understand too much at the quantitative level what happens as I march through these kind of branches. Okay, so it tells me some kind of criterion whether I can go further, but it doesn't really tell me much about the solution itself. Okay, so that's sort of where kind of the usual techniques fail in this setup. Okay, now this is sort of more related to Camilo's question. This is taken from the paper of Hosseini, Masmoudi, and Wheeler, and there are many variations of this. So if we are close to the disk, then the patches, these are the things that you obtain in the 3, 4, 5, and 6-fold branches. The patches kind of look like this egg-shaped thing, roundish and convex. Okay, so these solutions are all close to the disk. However, if you keep going through the branch, and then if you go further and further from the disk, then, okay, for the 3-fold case, you're still convex. For the 4-fold case, it's hard to tell. And then for 5 and 6-fold, you are clearly non-convex. Okay, so these are the things now that we are chasing in order to showcase that that convexity may be lost as you go through the branches, in particular if you are like in this 5, 6, and so on and forth. Okay, we're going to do one instance of this.
Wait, I'm trying to just understand the figure. So you've got the outer circle and you've got the domain.
No, forget about the outer circle.
Yeah, it's the outer
like
is just to kind of somehow figure out how to compactify.
No. Just look at this. This is forget about the outer thing. The outer has to do with the streamlines of the flow.
Okay.
So we are looking here at the boundary of the patch, and the boundary of the patch is given by this, the furthest contour inside the gray region. Okay, the other things are other properties that they wanted to highlight, but for the purpose of what I'm trying to say, they are not relevant.
And so somehow these are numerical computations that
Yeah.
are related to that theorem on global continuation or something of that sort.
Yeah, so these are numerical continuations, but numerical computations. But this is the paper from the global the global continuation result. But the global continuation is not quantitative. The global continuation tells you like everything is going well until something goes wrong, and there are a list of things that could go wrong, but it doesn't give you more information beyond that type of information. Okay, so this is what we proved. We took the six-fold case, and then we proved that for a given omega naught that we provide, for sufficiently and a sufficiently small neighborhood around it, we can find a non-convex V state that furthermore has analytic boundary. Okay, so we could find one instance of a non-convex V state in some small neighborhood of, let's say, a given omega naught in the six-fold branch. This is what we are aiming to prove, and this is what I will show how to. Okay, so let me show how to prove it. Okay, so the first thing is sort of to reduce everything, remove the time dependency, and simplify the problem as much as we can. Okay, so first we're going to write the boundary in polar coordinates. Okay, so we're going to pretend that z is r times cos and r times sine. So the vector z is going to be the vector r cos, r sine. Omega is still free and something that we need to figure out as part of the problem. So what we end up getting is this, well, horrible looking equation where we have the rotation term, which is nice. So we have r prime times omega, has to be equal to the singular integrals that are kind of nasty here and that we need to deal with, and that they have the logarithmic singularity and so on and so forth. Okay, so this is the real enemy here that we're going to have to be dealing with if we try to say something about r and something about omega. Okay, so this is the plan. We're going to try to find functions omega r that solve this non-local equation. Okay, so abstractly, we want to solve f of r is equal to 0 for f being some functional. In this case, it's the difference between this left-hand side and right-hand side. So this is kind of the meta theorem. The meta theorem is, I won't tell you yet how, but suppose that I can find some explicit approximate solution R naught, which is maybe very complicated, but who cares? So suppose that for some reason, I have some inspiration and I come up with a guess, R naught, that satisfies this f of R naught, maybe not just 0, but let's say small. Then what I'm going to do is to try to find a correction to R naught. I'm going to linearize my equation around R naught, look at the differential. This is going to be the defect, and then my correction, which I'm going to call V, is going to be, so this nonlinear part is going to be quadratic in V. So the idea is if I can make it work, I am going to try to invert the linear part onto the nonlinear part and the defect. And if my guess was right, then this part is not going to matter that much. And essentially, I'm going to try to be equating something which is linear with something which is nonlinear. So in principle, I should always win, no matter how bad the inverse of df is. Okay, so if the defect is small, then I'm going to try to close a fixed point in this way. So I'm going to be mapping V to this number, which is constant, plus the nonlinear part, which if this is epsilon squared, and if this is sufficiently small, this is going to be a contraction that maps the ball or a small ball into itself. Okay, so that's the plan. The plan is to effectively show that this is a contraction. Okay, and this is not new. It has been used by many people, including myself, my students, and other people, like, for example, Chen and Hao in the paper. Okay, so so in this case, computing the approximate solution was relatively easy. There are other cases, and sort of like doing simple numerical continuation worked. We didn't have to put a lot of modes. Like 30 modes were enough. There are other instances where computing the approximate solution is difficult, but this was fairly easy. Okay, so now let's really look at how this nasty equation will look like once we perturb around this approximate solution R0. So if I look at the differential, then what I'm going to end up having is these four types of operators. So one K1 that multiplies the derivative of V, K2 that multiplies V, and then some singular integrals acting on either V prime or V or V prime. Okay, so this is pretty much how this DF looks like, and yeah, the most singular is this guy. Okay, and I didn't even specify what the K's are, but the K's depend on R0. For example, this is a small fraction of how K1 looks like, just to give a feeling of how, let's say, unpleasant this kind of calculation looks like. Okay, something important that we're going to be using is that K1 is strictly positive because the dominant part is coming from this R0, and this is small compared to that. Okay, so I'm going to be dividing by K1 at some point. Okay, so what's our goal? Our goal is to prove that DF is inverted or bound the norm of its inverse, and then prove that there is a fixed point via the scheme that I described before. Okay, so the first issue, which is not really an issue, but we have to do something about it, is that if we don't do anything, the equation is invariant by dilation and rotation. So in principle, this DF, if I just set it up blindly, it wouldn't be invertible because there are infinitely many solutions arbitrarily close to R0. So I need to kill the dilation and the rotation symmetries. And I'm going to kill them by working in this space, essentially in the space of the derivative. So I'm going to assume oddness of this two, which means evenness of V. So by enforcing these conditions, then I can kill these symmetries, which is good because now the DF, at least is going to be, it could be invertible. Let's say there are no obvious issues that prevent DF from being invertible. Okay, so now let's rewrite everything in terms of U, and remember there was this V prime. So V prime is essentially U, which appears here, and then we have like a massive kernel acting on U. The good news is that this massive kernel is going to be a relatively compact operator. So that's going to help us a lot. Okay, so NL is epsilon naught, which is coming from the defect, and something quadratic, and now the operator after this transformation and so on, the operator that we need to invert is going to be of the form identity plus compact operator. Okay, so we want to invert L in L2. Epsilon is small enough. We'll need to make this quantitative. And then we will also have to fight with the Lipschitz constant of the nonlinear part. So if we succeed, and if all the numerology looks good, meaning that epsilon naught is sufficiently small, Then we can invert the linear part onto the nonlinear and close the fixed point in a small enough ball in L2. Okay, so the first thing we tried, which was possibly too naive, is to say, well, if the K is already fairly small, then maybe I can get away inverting I plus K by just doing a Neumann series. So that would be easy, but it's too good to be true. Because in our case, if we work in L infinity, this is bigger than 2. And if we work in L2, this is still bigger than 1.3. So a priori, we cannot do this trick of trying to invert the 1 plus K as a Neumann series on K. Okay, so instead, what we're going to be doing is to be approximating K by a finite rank operator. So we take some orthonormal basis of L2, and we approximate the kernel K by a finite rank kernel KF using this basis. So now this and N is moderate size. So now we're going to pretend for a minute that instead of having this integral operator K, what we have is this finite rank approximation KF. So now that's not so bad, because LF, which is I plus this KF acting on U as opposed to K, essentially the integral part is a matrix. So it's a big matrix, but it's a matrix. So that we know how to invert it. And the identity, we also know how to invert it. So if we manage to invert LF, and if we prove that the real L is close to LF, then we win. Okay, so this is how LF works. There is the finite rank part, the matrix part, and then acting on this space En. N is roughly 300. So this is the identity part. That's nice. And this is a big matrix that we need to check that it is invertible and provide rigorous bounds on the invertibility norm, on the norm of the inverse of this matrix here, I plus N. Okay, so if we succeed, then we can bound the norm of the inverse by the maximum of the top part and the bottom part. Okay, so we can do this by fixing a space of, let's say, moderate dimension, 300. We don't do this by hand, so we do a computer-assisted proof instead. Okay, so now if we manage to show this LF being nicely invertible, we want to use it to say that L is invertible, but then this is essentially corresponding to the tails of the operator. So the tails of the operator, because L and LF agree on the low modes, then L minus LF, since since K is relatively compact, then one should expect that LF will converge to L or KF will converge to K. So if we take enough modes, then this norm here, as the number of modes goes to infinity, will go to 0. So that's kind of the game that we play. By choosing the N sufficiently large, then these finite rank approximations get better and better, and this approximation error goes to 0 more and more. So in our case, and this is something we can do, we can bound the L2 norm of this operator by the L1 L infinity norm of the respective kernels. And in our case, this was enough to get some bound of this order, and this numerology is good enough to close. So here I stress that K is explicit. K was this kind of unpleasant integral that depended on R0, and KF is also explicit. It just has a very long expression that has like thousands of terms, but nonetheless, both functions are explicit. So when dealt using a computer, well, you maybe have to wait a little bit more, but everything here inside this norm is computable, and everything here is computable as well, and then you can get an explicit number once the N and the KF are fixed. Okay, so explicit but very complicated. We resort to use a computer system. Okay, so now let's see how to close. So this was the equation that we had to close. What is left to do, which is the let's say the pen and paper part, is to do quantitative nonlinear estimates to get the Lipschitz constant of the nonlinear part. This is something that we do by hand, or to some extent by hand, and then we get tight bounds using the computer again. So once we do that, then we have some condition on epsilon naught. Epsilon naught was the norm of the defect in a way that if epsilon naught is sufficiently small, then we can map the ball into itself and we can close the fixed point argument that we were trying to prove in the very beginning. So epsilon naught is really controlling how good our guess R naught and our guess omega were. And in our case, we can bound this quantity epsilon naught by a number which is of the order 10 to the minus 7. The difficulty is that computing this thing is expensive. The FIs have also integrals inside. So this is kind of a lengthy operation on a computer, but we were able to succeed and to run this in, let's say, within reasonable times. So yeah, same story, explicit, but very complicated integrals, even double integrals. We resort to a computer-assisted proof, and then the computer-assisted proof essentially says, well, epsilon naught or a bound on epsilon naught can be certified to be something of this magnitude, like this 10 to the minus 7. Okay, and at the end of the day, this is kind of what we can prove with a very precise estimate on the errors. So we can prove the existence of a solution of the form R of x equals R naught of x plus the integral of u, so that R of x is enclosed into these sort of curves where xk is one of these like middle points, these vertices over here. And this is really drawn to scale. Epsilon is roughly proportional to 10 to the minus 5. And from like through the naked eye, it is not even possible to tell the difference between the upper bound, the lower bound, and the actual solution. Okay? So we were able to obtain quite precise estimates, quantitative estimates, on the type of solution that we were proving its existence. Okay, so let's see what we have to do in order to prove the non-convexity. So up to here, we only have existence in some, let's say, low regularity L2-based space. We haven't said anything about the analyticity, and we haven't said anything about the non-convexity. So how to go first in the non-convex direction? Okay, so the good news about this kind of result is that we are proving that something is non-convex. So if it is non-convex, convexity only has to fail in one point, at least. Meaning, if we can prove that it is non-convex at one point, then we're done. If we were to prove that things are convex, then we need to prove it for all x, which is much more difficult, because then we need to go potentially through some C2 norms, or at least some norms on the second derivative of the solution. Now here we can get away with cheap bounds in L infinity, and that will already tell us that there is a point that is violating the convexity requirement. So one can do it in two ways. The first way is kind of the way we did it. So as long, if I drew a ray from this point to this point, and I look, maybe I can draw a picture. This is sort of an exaggerated version of the solution. I draw this line connecting these two dots. If this point is below the line that I drew, then the patch is non-convex. So this is precisely what this algebraic constraint here is suggesting, or is suggesting to prove. And this is what we check. Then because we had like all these bounds in L infinity, when plugged into this inequality here, we can check that at this point, even taking into account all the errors and so on, we're still below this line that connects the two vertices. Okay. And there is also another method if we had used other types of spaces, which is a nice idea. And essentially says that if I look at all the free space, that I have here in L1, if I were to be convex, all this space needs to be filled, because otherwise there will be a point at which the interface is non-convex. So the norm, the L1 norm of the perturbation needs to be able to fill all this gap that is between these 2 points. And the L1 norm of the perturbation is fairly small and much smaller than the gap that it needs to fill over there. Okay, so that's a slightly different potential proof of the non-convexity. Okay, now let's go from the non-convexity to the analyticity of the interface. Okay, up to here we had a solution in H1, and we want to go from H1 in principle to analytic. Let's go first from H1 to C infinity. In order to go from H1 to C infinity, what we're going to do, we're going to bootstrap the regularity. So we're going to write, by taking enough derivatives of the equation, we're going to be able to write k+1 derivatives, and we're going to be able to control them by some function of k derivatives of R. So if we can do that, and these numbers don't degenerate in this case, then being ck implies being ck+1, and being ck+1 implies being ck+2, and so on and so forth. Okay, so that's kind of the game to go from H1 to C infinity. Here we are using this ck1, the strict positivity of this constant ck1, which is the lower bound on k1 that I discussed before. And for such a ck1, I can always pick a delta in a way that this stays uniformly positive, and I pay with this 1 over delta here. But at the level of the quality of the estimates, I don't care anymore how bad the bounds on the kth derivative are, as long as those bounds remain fine. Okay, so this is essentially how to go from H1 to C infinity by applying this kind of scheme repeatedly. And then from C2 to analytic, we don't even need to go to C infinity. From C2 to analytic, one can use elliptic estimates in the version of Kinderlehrer, Nirenberg, and Spruck, that under some non-degeneracy condition, which is satisfied, essentially upgrade the result from C2 to analytic. Okay, just to give a small taste of how these estimates look like. So this was what we had on the left-hand side. We take k derivatives of this k1 r prime. The leading term is k1 dk plus 1r, and this can be lower bounded by this constant ck1 dk plus 1r. So that's like the easy term. And then a prototypical term on the right-hand side looks like this. This is after one derivative has hit on the log. So remember, we had something like log of a times something like this. So if the derivative hits the log, we're going to have something like a prime over a times something like this. We still need to hit it with k minus 1 derivatives. The worst, or one of the worst terms, is when all k-1 derivatives hit here. So effectively, this singular integral here becomes like 1 over z times k derivatives of r minus k derivative on x minus k derivatives on r at x minus z. So we can just bound this by splitting into the singular part when z is very small, but we make this region to be as small as we want. This, we pay the price of bounding it by the derivative. And then in the z large region, or not small region, then we get this 1 over delta factor to compensate, but we can just take L infinity bounds because there is no singularity anymore. And this 1 over z can be bounded by 1 over delta. Okay, so essentially this, we can absorb it with this CK1, and then we are good, because then we have managed to put all together all the high norms on the left being multiplied by a small number, not a small number, a positive number, and then all the low derivatives on the other side of the equation. So we can effectively prove things like of this flavor. Okay, so that's pretty much how the bootstrapping works for this kind of problem. Okay, so I had a few slides about explaining how we do the computer-assisted proof part. Let me skip them because I'm sort of tight on time. But just to come up with some final observations. So one could upgrade our results to say something about like the linear stability of this type of solutions, which is not known, but we have done essentially all the numerical study of the kernels that appear on the paper. So it shouldn't be terribly difficult to say something about the linear stability of these solutions. And we picked m is equal to 6 because it was, well, it had to be bigger than 4, and 5 was a prime number. So when it comes to like the reductions and the symmetries, 6 seemed to be much more friendly. So we picked 6 for that reason, but there is no other reason beyond that. And there is also nothing special about Euler. So one could try to do these kind of constructions and this kind of analysis for other equations like SQG or modified SQG. Like really, the multiplier will change a little bit, but the method and the procedure should also work for those kind of equations as well.
So you mean still looking at
rotating solutions like towards the end of the branch. But in general, for any, like, what did I use here about the rotating solutions? Nothing, in the sense that, okay, that they were steady solutions in that frame of reference. But if you were to look for self-similar solutions, this is omega plays the role of the self-similar scaling. So yeah, those are steady solutions in that frame of reference. And of course, every equation has its own sort of associated linear operator and so on and so forth. But from the methodological point of view, there is really nothing very explicit or very important about working with rotating or translating or steady solutions. The point is that there's no time here. And that is something important. But besides that, anything that is steady in some frame of reference, in principle, could be amenable to these kind of techniques and these kind of like estimates parallel with a computer.
Mm-hmm.
So yeah, let me stop here. Thank you very much.
Other questions?
There are these spirals that I don't know if there's a proof, like by Carden. Do you know the Carden?
Yeah.
What's the status of, like, does that fit within your category? Is that like, what's the status of that?
Yes.
problem?
So there are the constructions of the spirals. Yeah. No, there are many people who have worked on that.
Yeah.
So there is the work of Volker Elling, Well,
Yeah,
first
exactly.
Caden and
No, but Ellen was
Pauline.
looking at it kind of seriously.
Yes, so Ellen wrote a series of papers on this. Presan and his collaborators also wrote a couple of papers on this. I wrote one paper on computing this kind together with Claudia Garcia. In the case of not Euler, but modified SQG or generalized SQG. So people have managed to and then there is Hyun-Jun, who's a student of Alex Enescu in Princeton, also has results on this kind of matter as well. So it is quite active, and people are trying to find either things with different regularity, different sort of growth rates and decay rates of the spiral. So it's still quite active.
So is it methodologically within like?
You could do that. Yeah. In principle, you could
Because
do
it was
that.
very delicate. Like it was kind of similar. It's like around the same time as the thesis from Caltech. I think Pullen and like people at Caltech were kind of looking at this one in the same way. And the computations were not satisfactory, actually. I remember looking at it feeling like.
That's right. I mean, from the point of view of what you have to prove, if you want to prove it for like a single instance, let's say, or a perturbation of a single instance, then definitely you could do things like that, assuming that you figure out what's the right space and what's the right weight and all that. But in principle,
That's your problem, though, right?
It's not, yeah, exactly.
Coordinates are, well, it's unbounded, but you can still get away with that, and you have to work in some sort of weighted spaces.
Yeah, that's what I was thinking, right? I mean,
that's still all right, but then you have to work in this, at least Ellen and the papers after had to work in some sort of adapted coordinates to the spiral, which are tough, but you can do that. So for us, like at least for me, we did the paper, we wrote the paper using pen and paper methods, and it's a long paper, it's like 80 plus pages. But I think this could be amenable if your interest is to prove a single instance of like such a solution, like what Ellen and other people can achieve through essentially bifurcation methods or implicit function theorem methods, is a more generic sort of result. Like they prove that there exists a small ball sufficiently small such that anything will lead to that.
I'm asking just a more pragmatic sense of being able to see it and knowing that this is something that rigorously exists, which was kind of for me the gap between the numerical computations. And
some of these things you can actually prove that they exist. Then it really depends on the particular experiment and so on. But some of these things have already been proved.
There are questions. But in that direction, so how far would one be, like, because at least I saw, like, this is I think what Alberto and his collaborators are kind of expecting, that some of these would be actually asymptotic to
spiral. I mean, there is the question
like the line, and then this would become like a bifurcation from the from the steady state, but providing a second solution for the vortex field. But I guess that's the point at which you're stuck is like proving that the thing is really decaying at infinity, I guess.
Yeah. So for them, well, okay, I don't know what is the struggle for them concretely, but I would imagine that for such a problem, because it is unbounded, you're essentially trying to you want to prove non-uniqueness. So you have like data at infinity, and then you want to construct like two solutions for which the data at infinity
is the same.
Matches. Exactly. And then in one solution you have one spiral, and in the other you have two spirals. This is sort of the expected, let's say, thing that you want to construct. Now the issue is that you are trying to sort of connect the good asymptotics that you have from the Ellen or others construction in like towards the origin with things that like asymptotically at infinity. And then the matching in the middle is what is really difficult. Like you can understand the exterior problem, relatively okay, and you can understand the interior problem relatively okay, but figure out cooking up an initial condition in a way that these two things match is difficult. For me, I would say that this is presumably the hardest part of this kind of business. And what I presented would, in principle, apply. I mean, it would apply more towards the interior problem, but you can try to make it work. But of course, in that case, it's a lot harder. So to summarize, can it be done? Yes. Is it as easy as this? No.
Mm-hmm.
That would be my take on this sort of spiral, non-uniqueness, etc.
Could it also be that somehow, like, matching these things would somewhat be a non-genetic situation, like that, typically they would miss each other? Like that there should be also some...
Maybe.
But
at the end of the day, you're only interested in constructing one instance, assuming that there is...
So you mean if you get close, you could still hope to kind of get some implicit function theory on closing the...
Possibly, yeah. Like because you're perturbing either analytic guesses or numerical guesses, and if you have done things right, then you should expect that something is out there. So in principle, you should be able to close. But this is all provided that you're doing the right thing, let's say.
Mm-hmm.
Okay, so other questions? Okay, let's thank Javier again.